Started. It is my great honor to introduce Raluca Popa, who is currently at ETH and will soon be at Berkeley. I think, given the length of collaboration, the list of collaborations there, she doesn't need too much of an introduction, given the breadth and depth of some of the work that she's done, which many of us are familiar with. But part of the focus of this entire project in the seminar is this question of, can we compute on encrypted data? How can we compute on encrypted data? And her work has really been at the forefront of this. I mean, CryptDB, if you want to read a stellar paper, please read CryptDB. It is absolutely fantastic. And so she's going to talk about some of her follow-on work to the CryptDB work and stuff that she's doing now on this very interesting question of building systems that compute on encrypted data. So without further ado, thank you.
Thank you, Phil. So I'm going to tell you about how to build systems that compute on encrypted data in a practical way. So really practical is key to this. And the problem we're trying to address is that compromise of confidential data is prevalent. And I'm sure you heard about it too many times in the news. So to understand what's happening, let's look at a representative scenario. Many applications store sensitive data in servers. And this data leaks from the servers for various reasons. By the way, can you hear me well? Because I'm soft-spoken. OK. So servers can run different systems. So there could be simple systems, such as storage systems, in which they don't really compute on the data. And this we can already secure today with encryption. OK, so we simply encrypt the data at the server with a key that the client has. So now even if an attacker steals all the data at the server, it's encrypted. OK, so that's a simple solution. However, the problem really lies with most systems that actually compute on the data. So databases, web applications, mobile applications, machine learning tools, all of these compute on the data. And here you can no longer just simply encrypt the data, because how are they going to compute on it? And this has been a big problem in systems for a while, and pretty much the whole systems community approaches this problem with using one strategy. So the idea is to try to prevent attackers from breaking into the server. So they store confidential data at the server, but they try to prevent attackers from breaking in and stealing the data. And this is how pretty much most data today is secured. And this strategy was implemented with a variety of techniques. However, the problem is that data still leaks even with these mechanisms. And that's because attackers eventually break in. So let me give you some example of common attackers and why they manage to subvert existing systems. So, for example, hackers notoriously break into systems by exploiting software bugs because software is complex. And sometimes they even gain root access to the server. More and more companies are outsourcing their data to an external cloud. And this means that the cloud employees can now read confidential company data, even though they're not supposed to. And actually, this attacker is really hard to deal with because it's an insider attack. So these people have legitimate access to the servers. So they're inside the shell of protection of existing mechanisms. So existing mechanisms don't even apply to them. And also, I'm sure you heard about it in the news a lot, that the government has been snooping on a lot of private data, sometimes by leveraging physical access. OK, so to summarize this slide, existing mechanisms do not protect against these attacks because they store confidential data at the servers, and attackers eventually gain access to it. So in contrast, I'm going to tell you about a different approach, namely to build systems that protect data confidentiality even when attackers get access to all the server data. And the way to make this work is the following. The idea is to have the servers store encrypted data, but be able to process and compute on it in a practical way. So here is what I mean. So consider that the server has some encrypted data, and I denote encrypted data with a lock, and the key is at the client. This is a great state because even if an attacker gets to read all the data at the server, it's encrypted. The question is, how do you compute in this case? So one strawman you might consider is the client sending the key to the server so that the server can decrypt the data and compute on the encrypted data the same as before. And then after the computation is done, it can throw away the encrypted data and the key. However, this is not secure because an attacker breaking into the system at the time when the data is decrypted and the key is there can steal the data. So instead, the idea is to have the server compute on the encrypted data directly without ever getting the decryption key. The result it obtains is also encrypted. It sends it to the client, and the client decrypts it. But notice that in this process, the key is never sent to the server. So the attacker never gets to see the encrypted data. So computing on encrypted data was already proposed in cryptography, and cryptographers constructed a scheme called fully homomorphic encryption. This scheme actually supports any function on encrypted data, and it has very strong security guarantees. But the problem is that it's very slow. It's currently 9 orders of magnitude slower than unencrypted computation, which is prohibitive for many systems. So in contrast, I'm looking into building practical systems. And what I mean by that is systems that combine real-world performance with support for a large class of applications and also provide a meaningful level of security. And achieving all these three together is quite challenging. And let me tell you the insight into why we can actually make this happen. So the insight is really a combination of systems and cryptography. So if you just take crypto naively and try to support your system, run your system on encrypted data with just naively using crypto, you end up using fully homomorphic encryption, or FHE, which, remember, is very slow. Instead, the idea is to start from the system, understand the system, understand what kind of operations it needs to perform, and then try to support each operation with a specialized encryption scheme. And here the specialization is key because this is what makes an encryption scheme fast. If it's specialized to a task, it can be fast, as opposed to a generic scheme. And you may need to use multiple such encryption schemes, one for each operation. In fact, sometimes you'll realize that the encryption scheme you need in the system does not exist, so you have to come up with a new one. So we came up with comparison and join encryption schemes for a system called CryptDB that Phil mentioned, and a multi-key search scheme for a system called Mylar that I'm going to talk about more later in the talk. So now that you have these encryption schemes that are reasonably efficient, the last step is to design and build a system. And here, there's really no recipe. You have to come up with new techniques. You have to do more research. And we'll see later in Mylar that it's really crucial into making the cryptography work and give you any security at all. But the point of this slide is that you can see why you can even hope to make this approach practical with this idea of using multiple specialized encryption schemes. OK, so what kind of practical systems can we build with this approach? It's actually quite a few common systems. So we were able to build CryptDB, which supports databases on encrypted data. So the database is encrypted, and the database server can process SQL queries on the encrypted database. We can run Mylar, which is able to run web applications on top of encrypted data. PrivStats and vPriv, which are able to run mobile applications on top of encrypted data. And actually, we have a bunch of systems coming up. So we showed how you can do machine learning classification over encrypted data, how you can do deep packet inspection, network middle boxes over encrypted data, how you can have an encrypted key value store and compressed key value store on encrypted data. But I'm going to tell you a bit more about this later. So right now, just to give you a sense of how this approach works, let me pick one system and go more in depth and talk about it. So last time I was here was for the faculty job interview, and I talked about CryptDB. So I'm going to tell you about the next system instead, Mylar. So the list is pretty long, so it means I have to keep coming back. OK. So Mylar is a system that is a web framework in which you can build your web application such that it protects data confidentiality against arbitrary compromises to the servers. So Mylar fits in the broad vision we talked about, namely, the server only has encrypted data. But the browser is the one who has the keys and sees plain text data. So in Mylar, each user has a key that the browser can access. And when the user inputs some sensitive data to the browser encrypts it, Mylar encrypts it in the browser, and sends it to the web server encrypted. Later, when the user fetches this data from the web server, the browser intercepts it, decrypts it, and gives it to the user unencrypted, as if there's no encryption happening at all. Okay. So there's been a bunch of work that proposed encryption in the server, in the file system community, in the encrypted databases community, and even in the browser community, there were works mentioning that one should use encryption. However, none of these works actually are sufficient to build real web applications. And here's why. So they suffer from the following drawbacks. First, they don't deal with active attackers. So if you have an active attacker at the server, he can change the source code of the web application. He can inject malicious JavaScript that then, when it runs in the client's browser, it just steals the keys, sends the keys to an attacker, or sends the encrypted data to an attacker. So in some sense, your encryption is useless. Another reason is that existing systems do not enable basic functionality needed by web applications. So for example, data sharing is very common in web applications. Or they do not enable computing on the data once it's encrypted. So Mylar addresses all these challenges through a set of techniques, through web page code verification, principal graph and certification, client-side web framework, and the new encryption scheme for search. And I will tell you now about each of these techniques. By the way, feel free to interrupt me at any point with questions. OK, so to actually exemplify and to explain these techniques, I chose a running example, a chat application. So here, users share chats. So for example, Alice and Bob chat about work, and Bob and Eve have a chat called party. But the point here is that only the users who share a chat should be able to see the contents of the chat and no one else. So to support this application, we have to tackle a few things. So here's our to-do list. First, the server should not be able to see the messages. Second, the users should be able to share the chat room securely, which is just what I meant. If Alice and Bob share the chat room work, only they should see the content of the room and no one else. Third, we should have a way to format messages, generate HTML pages. All of this happens in a chat application. And finally, a lot of chat applications enable searching over the chat for keywords. So we should tackle all of these. So first, you can kind of already see that by creating this list, we're following the insight at the beginning of the talk, namely identifying what are the core operations an application performs and trying to support those efficiently with encryption schemes. OK. So in order to support this, the very first question is, how do we even organize the web application framework to be compatible with encryption? And you might think about just taking an off-the-shelf web application framework such as Django, Ruby, and Rails. However, and that's what we did too, but it turns out that these are not compatible with encryption. So let me explain why. So in a typical web framework, the web page is generated on the server side from sensitive data, from the information about the current user, and the code. And this page, then the code runs in the web server, produces a web page, and that's sent to the client and runs in the browser. OK, so there are a few issues with this. First of all, let's try to encrypt the data and see if this could work with encrypted data. So the first problem is that now the code has to run on the encrypted data. And there are very few operations that we can do today efficiently on the encrypted data. So this severely restricts the computation that we can do in the web page. Second, it is much easier for the attacker to tamper with the web page. He can insert some malicious JavaScript into the web page And when that runs in the user's browser, it sends the keys and the plain text to evil.com. Okay, so basically, for these reasons, existing existing web frameworks are not compatible with encryption. So instead, the idea is to actually use a client-side web framework such as Ajax Programming Style and Meteor. In this web framework is much more compatible with encryption, and here's why. So first of all, the data and the code are separate. They come on different channels. The code is static. It doesn't change. Then the web page is generated on the client side. So on the client, from data, current user information, and code, the web page is created and displayed to the user. So because of this layout, we can much easily add encryption. Here's why. So first of all, we can easily add a code certification module in the user browser. This module, what it does is it checks that the code was not changed by an attacker. So we trust that the code written by the developer is not purposefully leaking data. And we want to make sure that an attacker at the web server does not change the code the developer wrote. So I won't tell you much about how the code certification procedure works, but at the high level you can think about, since it's static, since the code doesn't change, you can sign it and then you can check the code against the signature. But there's a bit more work to be done there than that. Now the second thing we can immediately do in this framework is we can add encryption. Because data comes on a separate channel from code, we can intercept it, encrypt it when it leaves the browser, and decrypt it when it comes into the browser. And it's much simpler now because it's not mixed in with code. Okay, so by just doing these simple steps, we already accomplished a few things in our chat application. First, the server cannot see the messages because they are encrypted at the server. Second, since it's a client-side framework and you can do some computation in the client's browser, you can do simple things such as formatting messages, generate HTML page. All of these don't take a lot of time for the client or resources, but they would be really hard to do an encryption. So now let's see how can users share the chat room securely. So Mylar needs to know what is the policy for data sharing. And the developer can specify it through something we call a principal graph. So this graph has nodes that are units of access control. For example, users can be nodes. In our case, the chat is also a node. An edge in this graph basically means that the user has access to, that the principal has access to another principal. Okay, so each node is a principal. So for example, Bob's principal has access to the principal of the chat party, and Eve's principal has access to the principal of chat party. Okay, so now let's assume that Alice wants to create a chat called work, and she wants to share it with Bob. Here's what happens in her browser. So she clicks a button called create chat. This button calls Mylar's API that creates a principal for the chat, for the room work. Okay. And automatically Alice gets access to the chat room because she created it. Now let's say that Alice wants to invite Bob to the room. Then she presses the button invite user on the web page, which calls Mylar's API for add access. And that gives access to the chat room work to Bob. Okay. Now the developer had annotated in Mylar that the messages are encrypted. And concretely how he does that is that he specifies in the database, he inserts a column with a principal identifier and specifies that the message should be encrypted for that principal. So in particular, the messages in a chat room should be encrypted for the chat principal. Okay, so now when Alice inserts sends a message as part of the chat room work, SSN is 32, this message, basically the send message function in the web application inserts an entry into the messages table for the message with the chat principal. And then Mylar automatically encrypts that message for the chat principal. Okay. So now that we basically specified the access control, yes?
So does this mean if I add a principal with the
prior messages because they were not a member of that group, or will they be able to read the
They will be able to read. They will be able to read. Yes. I'm gonna tell you next how exactly cryptographically it works. But if you add someone to the chat room, they can read all of the information. Okay. So now that we have the access graph specified, how do we enforce it cryptographically? And this is through chains of keys. So here's what I mean by it. Each user, each principal has a key. The users have a key that gets created when they create an account. Then each chat has a key too, and this gets created in the browser of the user who creates the chat principal. The server stores all the keys that are not keys of users, but of course it stores them encrypted, because otherwise it could get access to the data. So here's how the keys are encrypted. So the key for the chat room work is encrypted under Alice's key and separately under Bob's key. In this way, Alice and Bob will be able to have access to the key for the chat work and decrypt the chat. And similarly for the chat part, it's encrypted under Bob's key and Eve's key. So now, also the data is stored encrypted at the server and is encrypted under the corresponding chat key. So for example, as the message SSN is 32 is encrypted under the key of the chat work. Okay. So here is how Bob gets access to the contents of, let's say, the chat work. He asks the server for the key of the principal corresponding to chat work. And because that key was encrypted for Bob, Bob can decrypt the key and hence decrypt the message and see it.
So that encryption of the key for Bob was done by Alice when she gave Bob
Exactly.
the right to do it.
Yes. Exactly when Alice invited Bob and she said add access, that's when the key was encrypted for Bob and sent to the server. Right. Great. So notice how Eve could not, for example, decrypt this message because the message is encrypted under the green key and Eve does not have an encryption, does not have access to that key. Okay. However, an active attacker, the server, could try to give access to Eve in some other way. And here is how. When Bob, let's say Bob wants to send some messages to Alice. So he asks the server for the key of the chat room work because he wants to send a message to Alice. But the server is going to give him a different key. He's going to give him the key for the chat room party. And Bob is then going to encrypt his messages under that key. And Eve is going to be able to see those messages. So basically, the server cheats during key distribution. The user asks for a key, the server gives a different key. So to prevent against such attacker, our idea is to use something called the certification graph. So this has the same nodes as the principal graph, but the edges mean something else. They basically mean that the user certifies, a principal certifies another principal. So in this case, Alice certifies the chat room work by providing a signature with her key in which she says the chat room work has this key. This is really the key of the chat room work. And now, in Bob's browser, when he fetches the key for the chat room work, he just needs to check the signature from Alice and see that the key is valid and he didn't get another key. But of course, this still assumes two things. First is, how does Bob browser know that it needs to check a signature from Alice and not Eve? And how does it know which is Alice's public key to check the signature with? So to answer the second question, we rely on an identity service provider, which is a very simple service that simply maps usernames to keys, and is just invoked once upon user account creation. And this account just provides a signature saying, yes, this username, Alice, has this public key. So something similar to Google's OpenID, for example. Now, to check the second question, that the signature should be from Alice, we rely on the user. So basically, we give each principal a human meaningful name, such as Alice or work for the chat room. Then the developer must display the entire path of certification to the user. So for example, there's a chat room created by Alice. Then if the attacker creates also a chat room called work, it's going to be by Eve. And then we rely on the user to choose the right path. So the user should, if user wants to send a message to Bob as part of the chat room work, to Alice as part of the chat room work, he should select the right chat room and not one created by Eve. So this is the only change to user experience that we have in Mylar. Everything else for the user is the same, but they must check that they're really clicking on the right chat room. Okay. So we're done with data sharing. Any questions here? Yes.
Can Eve mask its identity in that prior slide and pretend to look like Alice so as to create confusion at the time?
So basically, yeah, so basically that cannot happen because we bootstrap all the trust from the identity server. The identity server provides a signature on username and their public key. And there's just no way that Eve can pretend she's Alice because she cannot sign with Alice's key. So we bootstrap all trust from that initial mapping of username to public keys. So she could not. Yes?
How do you handle cross-site request forgery? Because it seems as though if you're generating static pages, you can't have the typical token that you put in there. Is it just that whenever you issue an AJAX query, the server has to check that it's signed first, or how do you do it?
Yeah, exactly. So whenever you can check the signature, or you could still have random tokens. So you can still have part of the code doesn't have to be all entirely static. Certain parts of the code you can denote that they're random, but as long as they're not displayed to the user, so the user wouldn't be led by those into taking an action that he shouldn't take. So you could still allow some of that. We discuss in the paper. And actually, we built Mylar on Meteor, and Meteor already provides support for all the common attacks like that. Cool. Okay. So the final task is to support search. So the challenge with the search is that, if you remember, the data of each user is encrypted under different keys. So Bob was part of the chat work and part of the chat room party. And they had keys different keys because they were shared with different people. And how can now the server search for a keyword over data encrypted with different keys? So we actually have encryption schemes already in the literature for searching over data encrypted with one key. So here's how those would work. So assuming we just have the data encrypted for the chat room party, Bob is able to take a word he wants to search for, let's say place, encrypts it under the same key with some a bit different algorithm, sends it to the server, and the server can identify the match using these schemes. But if we want to use this in our multi-key setting, we have to repeat it for every single key. So we'd have to encrypt the word place under the different key and then send it to the server. And the problem with this is that it's actually very slow. Not because so much that Bob has to encrypt the data under each key, but because obtaining each key is a slow operation because it has to go through all the principal certification graphs and all the various checks that Mylar does. So it's actually a very slow operation. Instead, it would be ideal if Bob could just encrypt the word under his own key, and the server somehow magically be able to do the search over multiple keys. And that's exactly what our new encryption scheme provides. And the core insight of the encryption scheme is that it enables the server to adjust the encryption from one key to another so as to match the encryption in the database. And I'm going to explain a bit more detail. Our encryption scheme is based on elliptic curves, and it has this API, but I will only tell you about the unique parts of the API, delta and adjust. So basically, in each user's browser, some deltas are computed. What are these? Well, Bob has access to the chat room work and the chat room party, so he creates a delta between his key and those keys, okay? And these deltas are then stored at the server, okay? So now these deltas will be used to adjust the encryption. Here's how. When Bob searches for the word place, the server can use the delta to adjust the encryption of the word from black key to green key, and then it matches the encryption in the database. It can similarly do for the purple key, and then the server can identify a match. So basically, what we did is we mapped the multi-key problem into a single key problem by enabling the server to do this adjustment using the deltas. Okay. So now all that Bob has to do is encrypt the word under his key, and he's done. Okay. So this was the search, and we're basically done. We're able to support the chat application. So in terms of confidentiality guarantees, Mylar protects data confidentiality of a user A against full server compromise, against compromise of other users' machines, as long as she did not purposefully share data with those users. And all this assuming that the developer's client-side code does not purposefully leak the data. Of course, the code could try to be changed by an attacker, but the original code of the developer does not try to send data purposefully to some adversary. And Mylar does not protect against side channels or access patterns and does not hide metadata. It focuses on hiding data content. So I'm going to tell you about the implementation and evaluation. Do you have any questions about the design before I go into that? About any question about the search? Yes.
Let's go back to the static code. So this is it has static code, and then I can certify it. But I think, as Baron pointed out, there's this issue where there are times you do need dynamic code. And so is it then like I could say the dynamic code I have is just the token for the form, so I can verify, so I can't just do it that way. But what's to stop someone then from inserting other dynamic code? Once you allow some dynamic code, why doesn't that open?
No, so we allow the tokens, for example. You don't allow dynamic code. You would just, for example, allow some holes where you can put some random value, but that comes from the server. But you wouldn't allow, you wouldn't evaluate, you wouldn't allow actual code for that. It's escaped. That part is escaped.
So I mean, there's certainly lots of applications today where you do want and use dynamic code. So in some ways, this is a restriction, but I mean, like.
Yeah, so here's the thing. So it is in some sense a description, but here's what you could do in Meteor. In some cases may be efficient, in some cases you may not. You generate a dynamic code on the client side. So you have some meta code that's fixed, that you anyways run on the server side to generate that dynamic code. And how do you generate that dynamic code? It's based on data from the database, right? So you send that data from the database, you send that meta code, and you generate the dynamic code on the client side. So that would be. Now, the question is it always efficient? Depends how much data you have to ship and how long the code runs. But
Have fun debugging that.
I don't know. Why would that be harder?
The fact that now suddenly the execution's in the client even more so depend on not only the combination of the code and the dynamic appearance of data, perhaps it's time interleaving, et cetera. But I mean, at some point, if they can do everything right, then it's very hard to secure. So these restrict the system.
Right. So I agree it's a restriction, but I actually don't. If you have an example, a concrete example in mind where this wouldn't work, I'm curious.
Oh, it's not a question of trade-off. Right?
Yeah.
Clearly it would work.
Yeah, it's clearly a high-level trade-off. I would like to know a concrete application where it shows up, and I believe it can be. But yes.
So I didn't totally understand where the savings were from the I don't remember what the name for it was, whatever the search crypto system. So the premise was that the expensive part is getting all of the keys in question.
Yes, and certifying them.
And certifying.
Yes.
But it must be like in different stages or something like that. So I just don't. I think I just don't understand it. But presumably here in this system, Bob still has to get all of the appropriate keys for each chat room in order to do the.
But the delta, you mean the delta? Yeah, but the delta is just computed the first time when he gets access to the chat room or when he creates it. That's when he computes the delta and uploads it, and then he's done. From then on, he really doesn't do much work.
So if the number of keys were very small, you could imagine Bob just storing all those keys locally somehow. But presumably that's not.
Yes, but think about it. This is a web browser, right? I mean, you go and log into a different web browser. You don't have state. There's no state here. Cool. So in terms of implementation, we implemented Mylar on top of Meteor, which is a really cool platform. You should go and try and play with it. But the design is not limited to Meteor. It really just requires this kind of client-side model and data and code separation. And it's 9,000 lines of code, JavaScript and C++. Funny combination. Okay, so in terms of evaluation, we try to answer two questions. How much developer effort does porting applications to Mylar require? And what is the performance overhead? So in terms of developer effort, we looked at a bunch of applications. Here are some on the slide. So for example, a chat application is the one we talked about, where you want to secure messages. Then we looked at the endometriosis application, which is actually a medical application, having information about patients that suffer from the disease endometriosis. And it's actually right now deployed by Newton Wellesley Hospital, and it runs with Mylar. And in here, you obviously want to secure a lot of medical fields. Then we looked at the class submit website, where you want to hide grades, homework, feedback, then photo sharing, where you hide photos, and so forth. The nice thing to see is that the number of lines of code added is actually quite small, around, on average, 36 lines of code changed to port this application to Mylar. Of course, these applications are already written in Meteor. But this number of code, the lines of code, are to add the security policy and get the security guarantees from Mylar. Okay. So in terms of performance, we looked at the chat application, for example. And this graph shows you the latency in milliseconds for the different operations in the chat application for the vanilla KChat application and for KChat with Mylar. So the first thing we can see is that the most common operation is transmit in a chat, sending a message and receiving it. And for that, Mylar adds on average 50 milliseconds, which is not noticeable by end user. Then for the join room and invite operations, Mylar adds a bit more overhead. And that's because these involve adding access to people and involve certifying keys. So these do principal graph operations. But still, they're virtually not affecting user experience. And in terms of throughput, Mylar reduced the throughput of the server by 17%. Okay. So I'm going to sum up Mylar. So basically, Mylar is a web application framework that protects confidentiality against full server compromise. It can secure real applications with a small number of lines of code, and has a modest overhead. And it does this through a set of techniques, such as web page code verification, principal graph and certification, a new encryption scheme. And Mylar is available, so you can play with it. So basically, I'd like to zoom out into the bigger vision that Mylar is part of, namely building systems that compute on encrypted data. I mentioned that we managed to build such systems for databases, Mylar for web applications, and PrivStats and vPriv for mobile applications. And now we have a set of really exciting work coming up. So first, we show that you can actually support machine learning classification efficiently over encrypted data. And this works for most common classifiers, such as naive Bayes, SVM, decision trees, combine them with AdaBoost, and so forth. Now, we're building two systems called Blindbox and PrivMB, which basically enable to run network middle boxes over encrypted traffic, so HTTPS traffic. And we show that you can actually do intrusion detection, you can check for exfiltration attacks, you can run firewalls, NAT, all over encrypted traffic. Another project that's coming up is we're showing how you can do big data analytics over encrypted data. And here you need to do more complex operations than I showed you in Mylar. And also another big problem is that big data relies heavily on compression, which is at odds with encryption. So we show a way in which you can actually make this work together, compression and encryption. And one of the big challenges for the next few years is to secure the Internet of Things. And I actually believe that in this setting, using this idea of building systems that compute on encrypted data, you can actually solve a lot of interesting problems. So, yes?
Can you go back to the compressing encrypted data?
Yes. Mm-hmm.
So can you just give me like one sentence that says what you're doing?
Yeah.
I'm not sure.
Yeah. So encrypted data, it's not really possible to compress because it's random. But you can compress data with certain algorithms that have certain structure and then encrypt the different small bits in that structure. So basically, you compress and then you encrypt.
That I believe.
Yes, but it's not so simple because if you compress, let's say, n files together, you obtain one compressed chunk. And if you encrypt it and give it to a server, you lose any functionality. You can't pick up the second file. You can't do anything on them anymore. So what we do is we have more clever compression algorithms that maintain some compress the data, maintain some structure, and then you just encrypt certain bits separately. So you can still fetch a file without decompressing and decrypting the whole thing. So you can still run some operations. That's basically the bit.
That I believe.
I like when people don't believe the work first.
Yeah, yeah, yeah.
Because it sounds
you
magical.
can't compress encrypted data.
No.
So that's
Yes.
Encrypt compressed data in a useful way.
Exactly. In a useful way is crucial.
Actually, can you mention a little bit more about
Yes.
unboxing? Could you say you can, for example, do stuff over TLS?
Yes.
Are you changing the cipher suites for
Um,
TLS?
yeah, we're augmenting the TLS traffic with some encrypted, with the encrypted tokenized traffic, encrypted in a different way that allows us to learn, oh, is this does it match some snort rules for intrusion detection, or
So
does
your
it?
participation of the endpoint.
Yes,
Okay.
yes. But we still allow one endpoint to be malicious.
Yeah. Participation of one endpoint.
Exactly. Cool.
If not, I would have been very, very interested.
No.
Yeah.
In fact, if not, no intrusion detection protocol works. Forget about encryption, but the intrusion detection does not work if the two parties agree to be malicious because they share one key and they encrypt with a semantically secure encryption algorithm that probably can do nothing. So if one of them cooperates, we can use a fancier encryption algorithm that allows for detection. That's the idea. Cool. Okay. So basically, we all know, the overarching problem here is that there are a lot of devices that collect a lot of private data about us. Some of them compute on the data and obtain various results. Others send the data to a cloud for computation. And really the ideal security here is to provide an end-to-end security guarantee that has confidentiality, integrity, and so forth. And you can see how basically in this setting, using this idea of building systems on encrypted data can help you. So for example, the cloud shouldn't learn the data, right? Should get encrypted data and should compute what we want on the encrypted data. Or the devices that get certain partial data, partial computation results. They shouldn't learn anything beyond those computation results. So I believe there's a lot of interesting ideas here and work we can do using this technique. So, and I'd be happy to discuss with you more any ideas you have. And I'm done. Any questions? Yes.
I have a question about the performance graphs from Mylar. So those do those include network latency or no?
Which one?
Sorry,
Yes, everything. It's end-to-end.
Okay, great. So do you have an intuition or numbers or whatever for sort of how expensive the actual crypto is? Like
Yes.
suppose we didn't, suppose network was free and we didn't care how much the
Yeah.
latency
So yeah, exactly. So basically, the difference between Mylar and the vanilla app is just the crypto overhead, and that's 50 milliseconds for the common operation. Yes.
Mylar requires the presence of an identity provider.
Yes, actually, not always. So basically what happens is that if anyone can join a system, like Alice and Bob, and then I want to give access to Alice to something, I need to have a way to check it's her. And you have to bootstrap trust from somewhere, and that's what the identity provider is for. But some applications actually don't need it because they have some sort of static access control. So for example, the medical application, doctors create accounts for patients. And in that case, it's very simple because the doctor can sign this username with this key. So the doctor can certify the patient's account. So in some applications, it's not needed because there exists this authority that creates accounts. But if anyone can join a chat system, then you have to have a way to check that they're Alice and not Eve.
And in that case, what type of entity could be a trusted, authoritative IDP?
Right, so we were thinking of enhancing, for example, Google's OpenID, or you could use different services, depends on what developer trusts, what service. Yes. Or a cloud provider, yeah, that's the idea.
If the adversary compromises the identity server and then also changes the code for the delta and address function, can they recover the original keys?
So if someone compromised the identity service, then they can basically fake they're a different user than they're not. And they can make future data encryptions of future data that's uploaded into the system to be visible to them. Yeah. They cannot see the old data because they don't actually have the key. Yeah.
again.